Today I'm going to talk about the research of a patent infringement analysis approach based on patent knowledge graph-driven fusions of graph and image similarities. Contents are followed. Patent infringement analysis is becoming increasingly crucial as enterprises faces rising risks of intellectual property disputes. Some studies have applied clustering models and decision analysis models to support PIA. More recent approaches incorporate data analysis such as keyword-based similarity and patent citation networks to evaluate infringement likelihood. Research object of this paper is this study aims to propose a novel patent infringement analysis model that integrates graph similarities and image similarities using a patent knowledge graph. The model extracts entities and relationships from both patent texts and drawing to quantitatively evaluate infringement probability with higher precision. By combining multimodal data and deep learning techniques, the approach overcomes the limitations of traditional text-based methods and improves accuracy and consistency in PIA. PIA has traditionally relied on manual comparison of technical features based on legal principles and expert judgment. However, these approaches are inefficient and vulnerable to subject interpretation. Data-driven approach using external patient information are studied recently. Some researchers use keywords, IPC code, and citation network to analyze similarity between patents. Keyword-based models often rely on TF-IDF, wait terms, or co-occurrence frequency, and citation analysis construct patent networks using direct, indirect, or co-citation network. These methods, however, lack consideration for detailed technical content. Textual context of patents is transformed into vectors using models like word-to-vec and doc-to-vec. These models are efficient and adjustable, but they lack semantic relational understanding. Ontology approaches like SAO extracts subject, action, object triplets from text using NLP techniques. Models such as RePAC or CRFGPS provide more structured representations for functional knowledge. However, these models often omit positional relationships and require costly manual annotation. CNN or BERT-based model classify patent texts or predict novelty with greater automation. Although powerful, they still struggle with redundant noise and domain adaptations. GNNs covers patents into knowledge graphs and leverage global plus local structures, boosting similarity accuracy. Uh, Patents drawing captures features, structures, and functions. Multimodal frameworks fuse text and image features to enhance classification and retrieval. Nevertheless, direct fusions can cause feature space conflicts due to heterogeneous data structures. This is the framework overview. Proposed framework views GS and IS through a three-part pipeline: ontology constructions, knowledge graph building, and similarity-based infringement estimation. Part 1 is built on RFSL based on ontologies. Extract entity via fine-tuned linear models and detect structures categories in patent drawing using YOLO V8. Part 2 is apply word segmentations, post-tagging, and LTP to derive triples, forming a patent knowledge graph for each patent. Part 3 is collect authorized infringing patents, constructs GMP and IP datasets, trains deep models, and output infringement probability. First of all, data source as patent claims, beneficiaries effect text, and drawing are selected as multimodal inputs. The ontology defines four entity dimensions: requirement, function, structure, and location. Requirement is divided into target requirements and component requirements, which identify what problem is solved and by what device. Functions includes verbs and nouns, while structures and locations describe physical objects and their spatial relations. The schema defines allowable relationships among RFSL entities. These relations include as function, has position, connect with, and allow downstream reasoning in the knowledge graph. The instance represents a rare case of rolling equipment with extra terms like rolled round steel plates mapped to entities. By applying this schema instance mapping, complex pattern semantics are translated into machine-readable graph form. Next one is patent collections via IPC-based crawling. The study retries patents based on IPC, focus on technical structures, and excludes process-based patents. Python and Enjoy APIs are used to crawl relevant vertex patents. This stage ensures the data includes both linguistic and visual cues. And next stage is text preprocessing and cleaning. Patent texts are segmented into sentence and cleaned by removing boilerplates fair phrase such as according to the claims. Additionally, meaningless numeric labels often found in structures claims are filtered out. This step improves consistency and semantic clarity before name entity recognition and phrasing. Patent claims are manually annotated using data in bio formats to label structures entities. For images, label image is used to draw bounding boxes around structures components like rollers or gears. These pair annotations allow text and image models to share aligned training data. A BERT's BiLSTM-CRF model is trained to recognize structures terms using embeddings and contextual decoding. The model archives robust performance in identifying complex technical expressions across various patterns. Contextual embeddings help capture entity boundaries and variation in expression. YOLO V8 is trained on annotated drawings to classify structures parts like gear with high accuracy. The model achieves about 90% suitable for detecting precise components. The use of bounding boxes and classes labels enable visual semantic fusions for downstream reasoning. The study defines two representations patterns for functional entities, abstract functions and specific functions. Verbs are standardized using predefined functions dictionaries, enabling consistency in entity extraction. The LTP tool is used to perform word segmentation, post tagging, and dependency passing on functional sentences. Synthetic patterns like verb objects and fronting object relations are used to extract structures, functions, triples. Location terms are often inconsistently described in patent texts. Each category is defined with examples and used to build a term dictionary. Location entities are parsed from structures, location terms, using RAD ATT synthetic relationships. These parse results are linked to the structure's entity and support spatial relationship reasoning in the graph. Patent invention text usually states the problem and the device that solves it in the first sentences. The target requirement corresponds to the problem and the component requirements to the device. Next one is nerve-based restrictions and summarization. BERT by LSTM CRF is applied to identify TR and CR entities. TR is summarized as an action goal and the CR as a device name. Eight types of triples are defined to organize six types of relationships among four RFSL entities categorized. The connect with relationship is subdivided into three types: direct connections, spatial relations, and functional co-occurrence. These triples are expressed as head entity, relationship, tail entity, which forms the foundations of the patent knowledge graph. Part of relationships are extracted from structured sentences describing hierarchical components. These patterns, such as component A consists of B and C, are recognized via post-taggings and DP analysis. For example, positioning mechanisms, parts of stress rows, and part of position plates. Connect with is often accompanied by head positions to reflect both connections and spatial relationships. Three types are identified: direct connection, spatial anchoring, and relative location anchoring. Dependency parsing is used to find relationships such as attribute, subjects to verb, and verb to objects. Functional relations are derived from beneficial effects text linking structures to abstract or specific functions. Triples are extracted using semantic patterns like structure drives objects or structure supports targets. These triples enable understanding of function structures relationships. The acquired by relations links a function to the structures that realize it. Need links a target requirements to the components addressing it. These relations are crucial for mapping patterns, intent, and realizations pathways. And all extracted triples are assembled to form a patent knowledge graph with edges representing syntactic relationships. The PKG is stored as semantic networks in Neo4j to support downstream analysis and entity reasoning. The first part involves constructing the dataset by collecting authorized and infringing patents along with their comparison documents, mapping the patent texts into graph networks. The second part focuses on training GNN and CNN models to calculate GS and IS, respectively, and building an infringement a probability model to analyze the likelihood of patent infringement. The notifications of review comments from Chinese patent examination information inquiry website served as a document for technical communications between patent examiner and applicants. It describes the reasons for the rejections of rejected patents and technical contents that are similar to those of the comparative documents. The dataset is divided into positive and negative samples. The positive samples are GMPs and IPs generated by infringing patents, while the negative samples are generated from authorized patents. A single patent may involve multiple comparison files, thus producing multiple samples. By utilizing GNN and CNN to calculate GS and IS respectively, a probability model for patent infringement is constructed. A SIMGNN is used for GS calculation, encoding patent text graphs into vector representations. For IS calculation, VGG is used to extract visual similarity from patent abstract drawing. The overall similarity score SIM is computed as sim is alpha multiple sim 1 plus beta multiple sim 2, where sim 1 is GMP similarity and sim 2 is IP similarities. After obtaining the similarity score, the infringement probability P is calculated using the following formula. Sim A is the average similarity between the new patents and its comparison set. Sim mean is the minimum similarity among infringing pairs. A higher p-value implies a higher probability of infringement. The steel pipe manufacturing industry is one of the most important metal manufacturing sectors globally. Patents tax related to welding devices were collected based on a steel pipe manufacturing company's needs. Trained Jiang and CNN models are used to predict potential infringement of newly developed welding patents. Patent text and abstract image are processed to extract triples and structure relations. The framework includes graph similarity, image similarity, and integrate them from infringement prediction. Using that IPC, welding-related patents from 2014 to 2024 were collected. After filtering, 2,321 patents remained and were processed using by-LSTM CRF. Patent images were labeled into structures categories such as support, transmissions, and driving. Image data was augmented and trained with YOLO V8. Functions and location features were extracted using dictionaries and LDP-DP parser. Manual tagging was used to define target requirements and component requirements. A total of 38,075 entities were extracted as visualized in Figure 17 and summarized in Figure 18. Based on the example in section 3.7, triples were extracted using DP results and semantic matching rules from the entities. Figure 19 presents a subset of these extract triples, demonstrating the resulting of various relationships types. At this stage, 92,323 triples were extracted from a large collection of patent texts. These triples form the foundations of a knowledge graph used for patent infringement probability calculations. Neo4j was used as the graph database to store the PKG of welding device patents. This enabled the visualization of knowledge and relationships within the domain of steel pipe forming equipment. Figure 20 illustrates examples of these visualizations using the construct PKG. A total of 3,552 patents in the steel pipe forming field from January 2014 to August 2022 were collected. After filtering and statistics, 2,730 patents were selected as comparative samples, including 1,292 negative samples. A Python-based preprocessors module was developed to convert claims text into graph formats. The SimGNN models were trained with these graphs using a batch size of 64, dropout rates of 0.4, and 150 epochs and learning rates of 1.10. Images from patent drawing were used to train a VG models for image similarity. The newly applied patents was compared with 5 existing patents. Text and image similarity scores were calculated using the GNN and CNN models respectively. Final similarity scores were weighted and combined using next formula. If the GS is lower than the defined threshold, infringement is determined. The newly applied patent's GS score was 0.3544, significantly below the threshold leading to a final infringement decision. The patent was ultimately authorized in June 2024. The implications of this research is the multimodal combining text and image archive, superior similarity calculation, and infringement analysis performance. Graph-based representations offer a clear hierarchical structures compared to Dr. and SE2 models. Also, SAO approaches captures functional and structural relations but are sensitive to semantic complexity. The limitation of this research is the accuracy of SAO-based methods varies significantly depending on sentence structure's complexity. The VGG image model is more suitable for design patents, not for structurally complex patents. Text-based models like Dr. struggle to extract key information from long, noisy patent text. Thank you for listening.